Swayam Prabha. Digital India. Educated India.
Hello everyone. In the next set of lectures, we are trying to discuss about mathematical logic, which provides a formal basis and representation of the arguments so that we could apply certain well-defined deductive rules to reach an outcome which is to be stated as true or false. In this lecture, we will try to see about the most elementary formalizations of such logic, which is called as propositional logic, and we will see some deductive system or the rules or steps by which we could conclude certain outcomes. The history and genesis of the logic spans across long back over the centuries ago. In different parts of the world, for example, in Indic or the periphery as well as in India, we try to have axioms and theorems in geometry and certain proof systems. Suddenly there are certain philosophers which tries to propose logical argumentations. There are Nyaya Shastra, Vedanta and formal systems which is being developed. In China there are philosophers like Confucius, there are school like Mohist school, and there are Buddhist systems which get originated in India, get transferred to China, and different other systems as well as. In Greek, we have Thales and Pythagoras, which gives us postulates of geometry and certain deductive rules to prove certain outcomes. Later, we have Plato, which formalizes logic beyond geometrical concepts. Finally, when we reach at the time of Aristotle, he first provides a formal basis and syntax of such kind of an elementary logic, which he called as syllogisms, and then it followed by Stoics and others. In Middle East, there are simultaneously some Egyptian logic and Arabic logic and inductive logic took place. In medieval Europe post Aristotle, there are subtle logic which leads to first order logics, which we will study in the next lecture. So amidst all these evolutions over the years in logic, we found that in today we are mostly concerned about certain types or the certain hierarchical structures of logic, which is propositional logic, predicate or first order logic, and higher order logics. And we see there are ample applications and domain wise improvisations such as in psychology, in philosophy, and also in many aspects. Why do we are studying logic? Because it gives us a particular basis or a formal tool for problem solving automatically using certain deductive rules or logical arguments. It aids in automated reasoning and learning, and in computer science nowadays there is widespread adoption of a newer branches of study like artificial intelligence and machine learning. We find logic plays a pivotal role to represent or to deduce or to represent an automated systems from where we could deduce certain proofs or derivations automatically. We will also see that logic is very much important to reason about circuit behaviors, and it is very much applied for verifying programs as well. Logic is also applied in cognitive models, assessment of them, and also neural network analysis. To start with, let us first see certain kind of arguments and try to figure out that how formal representations can be made out of these arguments and how we can think about manually by proving some arguments and how we can automate it and deduce it automatically. So my first set of examples related to IIT Kharagpur, like if I am the vice president of Gymkhana, then I am well known. I am the vice president of Gymkhana, therefore I am well known in IIT. So you can think of manually that it obviously follows that if I am the vice president of Gymkhana, then many of the people in IIT knows me, and if that is indeed the case, therefore I will be well known. Now the interesting fact, if you look at the example 1b, it's the same set of arguments that occur as we see in 1a. However, the person has changed. So I say that if Ninad is the VP of Gymkhana, then Ninad is well known in IIT. Ninad is the VP of Gymkhana. Therefore, Ninad is well known in IIT. So, if I could somehow represent such kind of arguments by formal structure, then the deduction for the first argument and the second argument both follows the same set of deductive rules. Because manually when we reason about, we follow the same nomenclatures and same set of rules to figure out whether Ninad is actually well known or I am actually well known. Whereas if you see the third example, 1C, it says that if Neha is the VP of Gymkhana, then Neha is well known in IIT. Till this can be represented formally as similar to A and B. But suddenly I say Neha is not the VP of Gymkhana. Can I conclude that therefore Neha is not well known in IIT? Here is, you can immediately figure out manually that something is missing here, because Neha may have certain accolades, or maybe some bright student, or maybe may have certain kind of contacts in IIT so that she is very well known in IIT. So therefore it does not automatically follow that Neha is not well known in IIT provided Neha is not elected as a VP. So how can we formally represent this, and how can we use the similar deductive rules to reason about the outcome? Let us come to a set of examples which is a little bit more complicated but on the same line. If Ninad is elected as VP of Gymkhana, then Ayushi is chosen as GSEC and Devang is chosen as a treasurer. Ayushi is not chosen as a GSEC. Therefore, can I conclude that Ninad is not elected as a VP of Gymkhana? By manual introspection, we can easily figure out that yes, Ninad has a pair of candidates called Ayushi and Devang. If I find out any of them is not chosen as GSEC, then obviously Ninad is not elected as VP. We will see formally how this reason can be formalized so that we could reason about the outcome. The second example, 2b, says that it starts with the similar premise that if Ninad is elected as a VP, then Ayushi is chosen as GSEC and Devang is chosen as a treasurer. But now I say Devang is chosen as a treasurer. Can I conclude by looking at only this argument, Ninad is elected as a VP of Gymkhana? I may not, because it may be the case that some other VP also has Devang, also thinks of Devang to be as a treasurer, even if Ninad is not elected but he or she gets elected. Therefore, only looking at Devang is chosen as treasurer does not conclude in a formal sense that Ninad should be elected as VP of Gymkhana. Let us now figure out that how we could encode this formally and how we could deduce this reasoning that we were trying to think about manually and come up with. So, the representation of propositional logic basically has two types of constructs. One is Boolean variables or propositions, we call it in formal sense, which could have true or false values. Therefore, we also call this kind of logic as zeroth order logic. And with respect to the propositions, we could define certain relations using connectives or connectors such as negations, conjunctions, disjunctions, implications, and sometimes we use if and only if. We will see that how if and only if is improvisation over implications, and we could represent using that. Each of these connectors or relations over propositions has a well-defined semantics which we can figure out from their truth tables. Our job to formally represent any of the argument or statements in the arguments is to represent using these propositions as well as these connectors and come up with a Boolean formula for that. When we obtain a Boolean formula, that's a combined formula for all the set of arguments that are present in the given statements, we try to obtain or try to prove or disprove those set of arguments or obtain the truth value of the combined formula, either using truth tables or using formal deduction rules, both of which we will show in the next few slides. Finally, we will try to see whether this is always true or there are certain cases where it is true but not always. That is, checking the validity and the satisfiability of the formula under all interpretations or all possible combinations of values of the propositions. Let us again revisit the example 1a and try to formalize and deduce it. If I am the VP of Gymkhana, then I am well known in IIT. I am the VP of Gymkhana. Therefore, I have to conclude that I am well known in IIT. First, let us see the propositions here are the simple statements that I can glean out from the arguments that are given to me. I am the VP of Gymkhana is, let's say, proposition V. It is true if I am the VP of Gymkhana, it is false if I am not. I am well known in IIT is proposition W, which is true if I am well known, it is false if I am not well known. The first statement now says that if I am the VP of Gymkhana, then I am well known. So we encode it using a formula called F1, which says if V, then W, which we call as implication. The truth table of implication is just a simplified version I have shown as an equivalent, that not V or W is an equivalent to saying it implication. And you can figure out the truth table of implication says that if V is true and W is true, then the V implies W is true. If V is true but W is false, then V implies W is false. And there are other two cases where V is false but W can be true or false. But try to think about that when V is false, my cause or the if statement itself does not hold. So I find that this particular code or formula does not apply in the world. Assuming the world to be true, we outcome it as a true. So if anytime I see that V is false, irrespective of the value of W, we say it is a vacuous truth in this world. So the premise does not hold means it's a vacuous truth. So now if you try to represent it using a simplified logical conjunction, we say that it is not V or W. Which means that if V is true and W is false, this particular combination, not V or W, is treated as false. Rest of the time it is true. The second statement says that I am the VP of Gymkhana. The formula is just the V because V denotes I am the VP of Gymkhana. Therefore, I am well known. That is my goal to prove, and I call it as a formula G. Now I have to deduce that formula F1 with or in conjunction to formula F2, can it imply formula G, which is simplified as this. If we go by direct truth tables, you can see that I have to reason about all possible valuations of V and W, which can take true and false both values. And I have to reason about this formula V implies W and V together implies W or not. So if you just write the truth table of V implies W, as I said, it is this true followed by false, true, true. And then V implies W and V results this one. And finally, I see that every possible valuations of truth for V and W, I get the complete formula everywhere as true. Therefore, I conclude that it's a tautology, meaning that I could blindly conclude that I am well known in IIT because there is no such scenario where I fail to conclude it. So the formula F1 and F2 implies G is valid because it is true under all interpretations of V and W or the propositions. By interpretations, I mean that an interpretation is a particular valuation set of all the propositions. So this true and true for V and W respectively is an interpretation where this formula is true. True and false is another interpretation where also this formula is true, and similarly for all of them. So we call it as a tautology or a valid formula. Interestingly, we find here a particular structure of representing formula that is abstract out from the statements or the grammar or the English or whoever is participating as a VP. Immediately it helps us as to keep the uniformity over the other example where it says instead of I mention as Ninad is the VP of Gymkhana. You see, nothing has changed in the deduction steps. Nothing has changed in the codification. It's only the interpretation of the formula is what we are considering here to make the outcome as true or false or to judge the outcome as true or false. Therefore, instead of I am, if I say Ninad is, everything, the representation as well as the steps of deduction using truth table remains the same. And hence, we could also say that this formula is also valid or a tautology. Now let us come to the formula which is a little bit wrong as we figured out manually. If Neha is the VP of Gymkhana, then Neha is well known in IIT. Neha is not the VP of Gymkhana. Therefore, can I conclude that Neha is not well known in IIT? Again, if we try to formally represent it, we code it as Neha is the VP of Gymkhana as V and Neha is well known as W. Now, V implies W as earlier for the Formula 1. Then for the Formula 2, we say that Neha is not the VP, so not V. Our goal is to conclude whether not W is true. That is, Neha is not well known. So our formula again, we are trying to deduce the formula F1 and F2 implies G. Now if I figure out in the truth table, what I see is that there is at least one interpretation which says when V is false and W becomes true, then the overall outcome becomes false. Which means there are scenarios where Neha is not the VP of Gymkhana, but Neha can be well known. See, here we abstract out the interpretations in such a way that I do not care about how Neha becomes well known. What I care about is the premise that Neha become VP of Gymkhana to be well known for her is not always valid, because there are other interpretations through which I can conclude that Neha may be well known even if he is not VP of Gymkhana. So therefore that particular interpretation says that even if Neha is not VP, which is V is false, she may be well known, which is true. So at this particular interpretation, I see the formula does not satisfy. This brings to a very interesting interpretations of the complete formula, which says that in the earlier case we have seen for all possible interpretations, if the formula is valid, that's a tautology. So this formula is not true under every possible interpretation. So it is not valid or invalid. Is it satisfiable? Yes, because satisfiability is defined as if there exists at least one interpretations among all possibilities of V and W where the outcome is true. We can see there are other three interpretations here where we found that this particular formula that we made is true. So therefore it is satisfiable. And unsatisfiable is just the reverse thing or the complementation of it, that it should be false under every possible scenario. So let me again reiterate the notions of interpretations, which is valid versus what is called invalid. So valid means at every possible interpretations, the formula, the outcome should be true. Invalid means there exists at least one interpretation where I found it to be false. So in this example, we find it is not valid and it is invalid because there is one instance where the formula outcome is false. Satisfiability on the other hand says that can I get one interpretation at least whether I can see the formula to be true overall? In this case, there are three such interpretations, so this is satisfiable. Unsatisfiability says that under every possible interpretations, I get the formula to be false. Here, this is not the case because it is only false for one interpretation. Therefore, if we try to have certain kind of formal representations, we can also have certain fundamental laws of propositional logics. Here I summarize through this slide all the laws. Let me discuss one by one. If and only if says whenever P is true, then Q is true, and whenever Q is true, then P is true. It is equivalent in saying that P imply Q as well as or and Q imply P. Double negation makes the proposition as true itself. So not of P is P. De Morgan's laws you must be familiar with, which can push this negation inside the whole bracket, that not P and Q both are occurring. It means either not P is occurring or not Q is occurring or both. Similarly for the OR case. Commutative law is just rewriting the proposition as in two different positions, that I say P to be true as well as Q to be true. It is equivalent in saying Q to be true as well as P to be true. Similar for the OR case. Associativity results that I can parenthesize a set of conjunctive propositions or conjunction of propositions in any order, as well as for the disjunction of propositions in any order. Distributive law tries to distribute the inner OR with respect to this AND. So it says P and Q or R, it becomes equivalent to P and Q or P and R. You have already seen this kind of interpretations where you draw Venn diagrams in your 10+2 levels. Idempotent is just saying if I 2 times conjunct similar propositions, it results the same proposition. Similarly for disjunction also. Identity says that if P is ANDed with truth value, then P remains as it is. It is equivalent to saying P. And if P is ORed with false value or contradictory values, then it becomes P as well. Inverse law says that if P as well as not P together means I am saying that P to be true and I am saying not P to be true. This cannot happen any point of time. So this is a contradiction. So we call it as a false. Similarly, P or not P is a tautology because you are saying P to be true or not P to be true. You are saying everything about the world to be true. Domination law says that P and F, that means you are saying that the world is false with this proposition, therefore the world still remain false. Whereas if you say a proposition is true with a true world, everything is true in the world, then obviously the outcome is that everything is true. Absorption law says that if we have P, we AND or conjunct it with P or Q, which is basically the unrestricted set because it says P can happen as well as Q can happen, but you are conjuncting it with P, which means only P can happen to make it true. So it's equivalent to saying similar for the OR case. Here I have used triple horizontal parallel lines to denote as equivalent to. In some books you can also find it as both directions solid arrows, which is also abbreviates as equivalent to. So with these fundamental laws, and we could deduce certain kind of formula instead of writing the truth table and checking for all possible valuations. Let's say there are n propositions, so we could have to write 2 to the power n possible valuations to check the truth table. We could apply these laws and can come up with a formula which is a tautology true or a contradiction F, or maybe which is not a tautology as well as contradiction but can be a satisfiable formula. So we use these laws to simplify the formula and reason about the final outcome. Let us again revisit a little bit complicated examples that we saw, that example 2a in our second slide. If Ninad is elected as the VP of Gymkhana, then IUC is chosen as GSEC and Devang is chosen as a treasurer. IUC is not chosen as GSEC, therefore can I conclude Ninad is not elected as VP. Let us try to deduce this using certain rules of or logical inferencing instead of truth tables, because as I already pointed out just now that if your number of proposition grows, the number of interpretations of the rows in the truth table grows, and therefore it is quite infeasible to manually see every possible outcome, making a tautology or a contradiction. So here I use V as the proposition for Ninad is elected as the VP, S as the proposition for IUC is chosen as GSEC. So S for the GSEC, T for treasurer and V for VP. So T is for Devang is chosen as a treasurer. So if I quote the first premise, it is if Ninad is elected as a VP, that is V implies IUC is chosen as a GSEC, that is S, and Devang as a treasurer. So there is an AND. So V implies S and T. The second proposition says IUC is not chosen as a GSEC. Therefore, I want to conclude that Ninad is not also elected as a VP. So formally, we try to say that F1 and F2 can produce the outcome G or not, and we write it in this way that F1 then F2 followed underlying, there is an underline, and we say therefore it is G or not. which is equivalent to saying that V implies S and T along with not S can imply not V. Now, if I try to logically try to justify using formulas or rules, I can say that what does V implies S and T means? It means that whenever V is true, S must be true as well as T should be true. So therefore, this rule follows that if V is true, then S is true. So if Ninad is the VP, obviously IUC is the G set. Now, so from the first formula F1, I can deduce V implies S. Now from the second rule, that is not S, if I try to take together with V implies S, it says that if V is true, then S is true, but S is false. Now, to make both of them true simultaneously, I have to conclude that my V is also false. Because if S is false, V is true, then V implies S, this first proposition becomes false here. But all the things that are on top of this horizontal line are assumed to be true. So to make both of them true simultaneously, I have to make V to be false. So therefore, I can see the goal has been reached by this set of formulas, and I can conclude, yes, Ninad is not elected as the VP of Gymkhana. Therefore, it's a tautology. Whatever the argument that you give is always true, and it's a tautology. So here we see an application of rules or the deductive process or system by which we could conclude certain outcome instead of truth tables as we have just seen before. The second example, if Ninad is elected as the VP of Gymkhana, then IUC is chosen as GSEC and Devang is chosen as treasurer, remains the same. Devang is chosen as a treasurer, Ninad is elected as a VP of Gymkhana. Can I conclude that? So let us see if Ninad is VP, that is V implies IUC as GSEC as S and Devang as treasurer T. Now the formula F2 says Devang has been chosen as treasurer. Now I want to conclude whether V is true or not. Similarly, we express this as F1 and F2 following G or not. So V implies S and T with T. If I assume this to be true, can I say V is true? You can see through similar kind of logical rules, I can conclude that V implies S and T means V implies T obviously. And with V implies T and T, I cannot conclude anything about V because V implies T is true, and if T is true, V can either be true or false. Because V implies true becomes true whenever V is true and T is true, and in every scenario where V is false, these are also true. So you cannot be definitive about the outcome of V, that Ninad is always elected as a VP of Gymkhana whenever you see that Devang has been chosen as treasurer. So therefore, I found out a scenario where there is a possibility that certain valuations of V, S and T is providing me the outcome goal as not of V. So therefore, I say that this is invalid. And invalid, if you remember, it means that there is at least one instance in the truth table where I found the outcome to be false. So here I can see that not V also satisfies along with T and some valuations of S. So if V is false, S is true and T is true, everything is satisfied, but the goal has not been reached. So this is an invalid scenario. So we saw some simple rules to come up with then arguments and a set of formal arguments to deduce certain outcomes to be true or false. So there are many such rules in which we could invoke and logically and could make out the outcome or deduce the system. So some of them are called like modus ponens, which says that whenever P is true, I say if P then Q and also say P is true. So therefore Q must be true. And if you try to write the logical implication, it is nothing but P and P implies Q. This whole thing will eventually imply Q. So this overall logical implication on the rightmost column is a tautology for our cases of rules. Modus tollens, we say that P implies Q and we say Q has not happened. So to have these two statements to be true, that P implies Q to be true where Q is false, it can only happen when P is false. Because if P becomes true, then P implies Q will be false because I made Q to be false. So P implies Q with not Q invariably imply that my P is false. And the logical implication accordingly says this way, which is a tautology. Syllogism says that P implies Q and Q implies R. It says that it is not of R. It says that it means that P implies R. So here P has been mistaken. So it will be P implies R. So I say that if P happens, then Q will happen. Then I say that Q happens, then R will happen. So eventually P will follow that R to happen. So it should be P implies R. So the right side says that corresponding tautology. Conjunction is a simple form that if my P is true as well as Q is true, then I can finally tell that P and Q both are true. Disjunctive syllogism says whenever I say P or Q to be true and I mention that P is false, so to have this system to be true, we must have Q to be true. Because unless both P and Q becoming false, making P or Q to be false. Contradiction says that whenever not of P implies certain falsification or contradiction, it means that I have assumed wrong thing, so my P should be true. This is similar, and you have also noticed when you prove something by contradiction, right? So you assume something to be true and reach a scenario where some behavior becomes false, thereby invalidating your assumption that you have made a wrong assumption. So it says whenever I made an assumption not P, I come out to a certain kind of form which becomes false. That means my not P assumption is wrong, so P holds. Conjunctive simplification means whenever you say that both of the things holds together, then obviously it follows that one of them definitely holds. So P and Q definitely imply P. Even if it is Q also, it also implies Q. Disjunctive amplification, if P holds, then obviously P or Q, it follows that P or Q holds. Because since P is true, it made P or Q to be true always. Conditional proof says that if I say my P and Q both are true together and I say P implies Q implies R. Now if P is true, so if P and Q are true, then obviously P should be true as well as Q should be true. Then if P should be true, then Q implies R must be true together. Now I also say Q to be true, then R must be true. So it follows that R is true. Proof by cases, it says that P implies R and Q implies R, which means that if I also make P true, I get an outcome as R. If I make Q true, I get an outcome R. So either of them, if it is true, I get an outcome R. So P or Q implies R. P implies Q and P implies R. It means whenever P is true, both Q and R together gets as an outcome. So it follows that P implies Q and R. Constructive dilemma says that P implies Q and R implies S, and I say either of P or R is holding. Then obviously my conclusion is either the outcome Q or the S should be holding. So that is what the constructive dilemma says. The destructive dilemma says P implies Q and R implies S, just like the constructive dilemma, but at the outcome I say that either not of Q holds or not of S holds. It means if either of them holds, it means that either of the premises that I made, P as well as R, either of them is false. So either not P or not R is the immediate conclusion. So using this set of rules, we can naturally set up a deduction system by which the formal representation or the Boolean formulas can be automatically reasonable. Now we will apply these rules and see how it happens. if these are new examples, by the way. If Ninad is elected as VP, then IUC is chosen as a GSEC, or note the change here, I have made and to an or. Devang is chosen as a treasurer. IUC is not chosen as a GSEC. I have to conclude that therefore, if Ninad is elected as VP, then Devang is chosen as treasurer. Let us formally represent and conclude it instead of manually trying to figure out and find a result. So similarly, again we see that V denotes Ninad is elected as VP, S denotes IUC is chosen as GSEC, T denotes Devang is chosen as treasurer. So my formula 1 says if Ninad is elected as VP, that is V implies IUC is chosen as GSEC or Devang is chosen as treasurer. So this is an or. Then I also mentioned that IUC is not chosen as a GSEC, which is formula F2. Then I mentioned that if Ninad is elected as VP, then let us assume that Ninad has been elected as VP, which is V as formula 3. Then can I conclude that Devang has been elected as a treasurer? That is, my goal is to conclude that whether T is true or not. So formally, F1 and F2 and F3 must conclude, therefore G is true. Or V implies S or T and not S, and if Ninad is elected as VP, then I will try to conclude whether Devang is Ninad's treasurer or not. So this is the requirement that we are trying to prove formally. Let us try to use those formulas that we have just shown, few of them. We call it as a logical inferencing in this setup, deduction setup. So first let us see that V implies S or T and my V is true. Then obviously S or T must be true, and which follows this way, which is the modus ponens. If I go back to the previous slide, you will see the first one. P is true. P implies Q is true, it follows Q is true. So I use that. Now I get S or T to be true. I see S or T and I have another formula not S. If I try to find what gives me S or T with not S, I see that S or T to be true as well as not S is true. So that means T must be true. Otherwise, S or T cannot be true. So this is where we use disjunctive syllogism. Again, if you see that this disjunctive syllogism here, P or Q and not P immediately imply that Q must be true. So therefore I can conclude that yes, the statements or argument that you made here is a tautology, that if Ninad, in this premise that we have set up, if Ninad is elected as VP when IUC is not chosen as GSEC, then Devang must be his treasurer. So this is how we call as rule-based deduction setup, and these are the set of rules that we have already discussed. We apply it one by one to deduce an outcome to be true or false. Let us see another example. The premise is the same, just I have tweaked it a little bit by saying that if Ninad is elected as VP, then either IUC is chosen as GSEC or Devang is chosen as a treasurer, but not both. So I will have one of them in Ninad's team, but not both. The rest is that IUC is not, the rest remains the same as per the previous example. IUC is not chosen as GSEC. If Ninad is elected as VP, then I have to conclude whether Devang is chosen as treasurer or not. So this is an exclusive or to that sense, that either IUC or Devang I need. So if Ninad is VP, V implies S and not T, that is IUC is as a GSEC and Devang as not a treasurer, or IUC not as a GSEC but Devang as a treasurer. So if Ninad is elected as a VP, either of these case can happen. So I encode this as F1. F2 and F3 are the same, which is IUC is not a GSEC and Ninad is a treasurer. Ninad is a VP. Then I have to find out whether Devang is my treasurer or not. So overall, I would like to find out this and not S and V is a treasurer or not. I left it you as an exercise to find out from the previous slides that which are the rules that you can apply, and finally where can you reach to whether you can conclude something or not, and or you can say it as a tautology, or you can say it is unsatisfiable, what you can conclude about or reason about in this particular arguments. Just to give you an hint, usually I have made to a color scheme like blue is for the correct or a tautology based argument, and red is for the rest, which is not a tautology or invalid arguments. So looking at the example color, you may have guessed that what will be the outcome, but it is always good to formally prove, and that is the goal of this course. Also, all these rules and deductive systems are very much useful to automatically reason out, and often we see that we can solve problems using this kind of deductive systems of propositional logics. Problem sometimes means that there are certain arguments to be followed up to reach certain goal or not, or to find certain goals to be true or not. Here is one such example. Let me first illustrate the example that you reached by walking in a maze or labyrinth, where you find in front of you there are three possible roads. The road on the left is paved with gold, the road in front of you is paved with marble, and the road in the right of you is paved with small stones. So you are at a junction from where there are three directions to move. One is a gold pavement road, one is a road with marble pavements, and one is a road with stone pavements. Now you also find there are a guard protecting each of these pavements, entry of each of these pavements. When you talk to the guards, they say this. The guards of the gold road says that this road will bring you straight to the center. So this road will lead you to the center, he says that. Moreover, if stone's pavement can take you to the center, then marble also take you to the center. So this is his claim. He says that this road will bring you straight to the center, as well as, moreover, that means in conjunction to this, he also said that if stones can take you to the center, then the marble road will also. You went to the second guard of the marble road. He suggests that neither the gold nor the stones can take you to the center. And the third guard on the stone road, when you ask him, he suggests that follow the gold and you will reach the center. Follow the marble, you will be lost. Now, if you know that all of the guards are liars, then can you deduce that which road you have to make to go into the center of this labyrinth? So your goal is to reach the center of the labyrinth. You reach at a junction where you find three roads, gold road, marble road, and stone road. There is a keeper or guard in the entry of this road. You ask each of them, they said some sentences to you, and you know all of them are liars. That is definite. It is known to you. Now, how can you find out? So, let us analyze this by using a simple truth table based method to reach our goal. So, first of all, we need to formulate propositions. We need to formulate the representation of each of these statements and need to set up our deduction system, so by which we could write the truth table or some kind of deduction rules by which we could find our goal, whether we can reach by the center through certain kind of roads or not. So here we go. So since I have three guards, my propositions are like that. GG means guard of the gold road is telling the truth. If GG is true, he is telling the truth. If GG is false, he is telling the false. And as I know that GG is always false because he is a liar, so I will always have not of GG to be true. Similarly, for the guard of the marble road is telling the truth is denoted as the proposition GM. The guard of the stone road telling the truth is denoted as the proposition GS. The gold road leads to the center is my G. Marble road leads to the center is my M. Stone road leads to the center is my S. Now let us try to formally represent the statements of each of the guards. So gold road guard says this road will bring you straight to the center. If stones take you to the center, then marble also take you. So look at the first one. So the guard of the gold road, if he is telling the truth, then gold road will take you to the center. And he also says, moreover, if stone road take you to the center, then marble also. I put an if and only because if the guard tells the truth, then the right side is true. And if the right side is true, it follows that guard must have told the truth. So therefore, I encode it in this way that this if and only, or it is equivalent to this. Whenever GG is true, this is true. Whenever GG is false, this is false. Go to the second statement of the guard of the marble road, that neither the gold nor the stone pavements will take you to the center. So it is encoded as nor gold, not gold, and not of S, which means that G is my gold road leads to the center, which is not the case, as well as and stone road is also not leading to the center. This is as per the truth of the middle marble road guard. The third one says that follow the gold and you will reach the center. Follow the marble, you will be lost. So the guard of the stone road says that gold road will take you to the center, marble road will not. So it is encoded as gold road will reach to the center and marble road will not. So these three are the propositions. These three are the Boolean formulas that are deduced out of the statements of each of the guards. Now let us see that what we know more. We know that each of the guards are telling lie. Therefore, not GG is true, not GM is true, and not GS is true. So I know my Z, this Z is true because I know that all of them are liars. So this is the case. Not GG and not GM and not GS. So eventually, as I have made an if and only or an equivalent relation formula, so I can immediately translate it into not of whatever I found out by their statements. The gold road statements is this, not of that. Marble road guard statement is this, I found a not of that. Stone road guard statement is this, and I make a not of that. So if I simplify by pushing the not here by De Morgan's law, I get this one. Because S implies M means not S or M. So when not get pushed in, it will be S and not M. Similarly for the other cases. Now, this Z, I know that they three are liars. So this Z is true. I have to find out what are the possible valuations this becomes true. So I come up with a truth table of Z and try to find out where it is true. So if you see here, there are three particular terms which I have conjunction with and. So these are the three terms, not G or S and not M, G or S and this. So Z should be true whenever these three are resulting to be true because they three are in conjunction. And if I go by all the interpretations of G, M and S, which is the only three participating propositions in my formula, I found there are 8, that is 2 to the power n number of interpretations. Among them, I know my Z is to be true. So therefore, I am only considering these true values which are marked as red. And when I see this, I immediately figure out that it says always gold is false here. Always stone S is true here. And always marble is either can be false here or can be true here. So there is no definitive answer. Now try to remember what this G, M and S stands for. It stands for the gold road will lead you to the center, the marble road will lead you to the center, or the stone road will lead you to the center. So as I know that the truth value of Z is what is my premise or what is to my knowledge, so obviously I see that it is encoded as not G or S. It means that definitely the case that gold road will not lead you to the center. As per the statements of the guards which are lying, stone road will definitely lead you to the center because the stone roads are true are in these two cases where I get the outcome true which I know. And about the marble road, I am not sure about, because it does not give me any definitive answer. So it implies that stone road will surely lead me to the center. So looking at this problem, I solve and reason about to find out my answer to reach the center of the labyrinth using propositional logic and simple truth table based deduction mechanism. I leave it as an exercise to you that how can you use our deductive formulas or the laws of propositional logic, that is modus ponens, disjunctive syllogism, etc., to come up with the same conclusion that we have made before. I leave it as an exercise to deduce using rules instead of using truth tables. So this summarizes the fact that it is a very useful abstraction of representing any argument using propositions or Boolean primitives and conjunctions, which helps us to make a deductive process or system to run, and therefore we can automate it using any machine. We can automate the overall process and can have logical inferencing to deduce our answers. However, this is a very elementary zeroth order or propositional logic which only deals about true and false values. There are certain limitations of it. There are certain insufficiency, or if you ask that whether everything can be encoded or not, the answer is not in propositional logic, obviously. So let us try to see some examples where propositional logic is insufficient. If I say wherever Ankush goes, so does the pet dog. Ankush goes to school, so dog goes to school. Let us see a second statement. No contractors are dependable. Some engineers are contractors, therefore some engineers are not dependable. So all actresses are graceful. Anushka is a dancer. Anushka is an actress, therefore some dancers are graceful. And finally, every passenger either travels in first class or second class. Each passenger is in second class if and only if he or she is not wealthy. Some passengers are wealthy. Not all passengers are wealthy. Therefore, some passengers travel in second class. The major problem of encoding this kind of statements directly into proposition is there are certain kind of phrases or words which is not like directly assigning a statement like meaning to somebody. Like, for example, let us check this one. Some engineers are contractors. It says that there is something called some. And in logic, either you say that I am an engineer, I am also a contractor, and you try to represent such kind of simple statements of Boolean values to be true or false. Here there are certain kind of quantifications involved, that wherever Ankush goes, so therefore Ankush goes to school, Ankush can go to library, Ankush can go to playground. So wherever is another quantifications that I must incorporate in representing this logic, so to deduce it over other kind of statements or outcomes as well. Similarly, every passenger either travels in a first class or second class. So we found there are certain deficiency in propositional logic in two cases, which limits the expressibility of these kind of statements or arguments in terms of such a logic. One is there is no way to define quantifications in propositional logic like some. No contractors are dependable, none of the contractor. All actresses are graceful. Every passenger either travels in first class or second class. Wherever Ankush goes. So these kind of quantifications over certain persons are not specified. Another thing is not specified, that Ankush goes to school or Ankush goes to playground is a functionality which relates Ankush and it's going to some place. So therefore it's not just a proposition to that extent. So Because if you look at the first statement, manually if we try to interpret it is obviously true, because wherever Ankush goes, his pet dog also go. Now the problem is that if I change the outcome argument as Ankush goes to playground and try to justify whether his dog goes to playground or not, you have to introduce another new proposition which will be different from saying Ankush goes to school. Ankush goes to library is another proposition. So therefore, you cannot, if you try to also deduce it in terms of propositions or reason it about, you say Ankush goes to school is my proposition P. Now Ankush goes to library, if something is says, it should be your proposition Q. Ankush goes to playground should be your proposition S. Rather, to uniformly represent it, if we have certain kind of attachment with respect to a functionality, like X goes to some place Y, it will be very easy or very convenient, as well as it is widely interpretable across different dynamic scenarios to represent the particular sentence. Similarly, Z travels in a train. So, if it is as I travel in a train, or if it is some other passenger travel in a train, so it is this functionality of traveling in a train may be incorporated using this. So, this is some of the limitations which we will see in the next lecture, that how a different order, first order logic or predicate logic can incorporate such kind of quantifications and functionalities into it, so that to express this meaningful arguments clearly without any ambiguity, and it also follows certain deductive rules to solve them. So we will see about the predicate logic or the first order logic in the next class. Thank you.